But since it's a totally new product with totally new, like everything is totally new.
Optimus V3's redesigned architecture has cut task execution time to under 6 seconds, nearly 30% faster than Gen 2. Every joint, arm, and controller has been re-engineered with a sharp focus on speed and stability. The result is evident in each fluid, deliberate movement. So, what sets this new design apart? Before we begin, please help us reach 13,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. How does Optimus V3 achieve 99% accuracy in complex tasks? Tesla Optimus V3 has reached a remarkable milestone: 99% accuracy in executing over 500 complex tasks in real-world environments. This figure is not only a bold statement about technological advancement, but also opens the door to a future where robots can work alongside, or even replace, humans in scenarios requiring extreme precision. But how did Optimus V3 achieve such a dramatic leap in such a short time since version 5.2? The answer lies in the fusion of optimized hardware, a sophisticated AI brain, and a revolutionary training process. First, let's look at the hardware foundation. Optimus V3 has been completely redesigned with a more precise, lighter, and faster reacting mechanical system. Its weight has been reduced to just around 50 kilograms, an impressive figure compared to most humanoid robots, which typically weigh over 80 to 100 kilograms. The skeleton, made of aluminum-magnesium alloy, maintains durability while reducing inertia during motion, which significantly improves flexibility and positional control in fine motor tasks like folding towels, picking up small objects, or sorting items in a kitchen setting. However, hardware is just the foundation. The core of the 99% accuracy lies in its real-time image processing and reflex capabilities powered by AI. Optimus V3 uses Tesla's latest generation FSD full self-driving chip, optimized to process hundreds of high-resolution video frames from its cameras in real time. Every movement and action is executed with advanced 3D spatial analysis and ultra-low error probability. Whether it's pouring water into a glass, placing dishes precisely, or handling fragile objects like eggs, the maximum position deviation is within just 1 to 2 millimeters, ensuring no breakage or mishandling occurs. Another key factor is how Tesla trains its robots. Unlike competitors like Boston Dynamics or Agility Robotics that rely on manually programmed behaviors, Tesla adopts a reinforcement learning model and human imitation training. Optimus has shown thousands of hours of videos of humans performing everyday tasks, from cleaning to cooking, and its AI infers the appropriate actions through observation. In a recent live stream, Elon Musk stated, "Optimus can learn a new task in just a few minutes by watching video, which allows the robot to acquire new skills hundreds of times faster than traditional industrial robots." Digging deeper, Optimus V3 software also includes a self-correcting feedback system. When an action is performed incorrectly, like grabbing the wrong item or being slightly off position, the robot corrects itself within seconds and updates its internal model to improve future attempts. This is a major reason why, after thousands of trial runs, the system consistently hits 99% task accuracy. In scenarios where the robot needs to wipe a table clean, neatly organize a cabinet, fold clothes, or navigate tight spaces, this level of precision is astonishing. To ensure long-term reliability, Tesla has implemented a performance scoring system for every task Optimus performs. Each action is rated based on criteria like positional accuracy, completion time, object safety, and energy efficiency. Only task sequences scoring above 98% are approved for mass deployment. This explains why Optimus V3 doesn't just do the job, it does it right and efficiently. Notably, Optimus is capable of prioritizing tasks within a complex sequence. When cooking, for example, it can start by turning on the stove or boiling water, time-consuming steps, before returning to chop vegetables. This reveals a deep level of behavioral planning already integrated into its AI brain. Another standout feature of Optimus is its over-the-air OTA software update capability, inherited from Tesla's electric vehicles. This means it can receive weekly AI updates, allowing performance to improve continuously without manual intervention. With this update rate, each robot can learn an average of 5 to 10 new tasks per week, meaning in just 1 year, Optimus can master up to 500 distinct tasks, ranging from simple to highly complex. Finally, we must highlight the critical role of real-world data collection. With thousands of Optimus units being tested in Tesla factories or simulated environments, every action, error, and rare scenario is logged and fed back into the training pipeline. This is Tesla's secret weapon. The more Optimus operates, the smarter it becomes. The more Optimus operates, the smarter it becomes. Once again, please help us reach 13,000 subscribers. This is important for us to stay motivated. Thank you. How has the new design of Optimus V3 enhanced its real-world performance? The redesign of Tesla's Optimus V3 isn't just a visual upgrade, it's a re-engineering of purpose. Every curve, actuator, and joint has been sculpted to serve a singular goal, mastering complex real-world tasks with near-human precision. Gone are the mechanical hesitations and jerky transitions of earlier prototypes. In their place is a robot that moves fluidly, adapts on the fly, and demonstrates an almost uncanny intuition for object handling, motion planning, and error recovery. The most significant leap lies in the architecture of its limbs and joints. The introduction of Tesla-designed actuators, built entirely in-house, delivers not only higher torque and speed, but allows for more refined control at low force levels. This precision is critical for handling fragile objects like glassware or folding laundry, tasks that until now were nightmares for rigid industrial robots. With these proprietary actuators, Optimus V3 can now pinch, grip, rotate, and release with remarkable finesse, thanks to sub-millimeter accuracy built into every motor encoder. But physical motion is only part of the equation. Tesla has integrated a new sensor fusion system into the robot's arms and fingertips. Tactile feedback now works in tandem with vision systems and force sensors, creating a closed-loop awareness that allows Optimus to instantly detect when it's gripping too hard, or if an object is slipping. This advancement is crucial in unstructured environments, where no two interactions are the same, whether it's aligning a dish in a drying rack or sorting fresh produce without bruising it. Crucially, Tesla's use of a neural network trained on real-world human demonstrations has transformed Optimus V3 from a motion-executing machine into a decision-making agent. The robot no longer follows static scripts. Instead, it interprets the context in real time. For instance, when unloading a dishwasher, V3 doesn't merely repeat a set of programmed motions. It identifies varying cup sizes, adapts its grip, determines the stacking pattern on a drying shelf, and ensures no overlap that might cause breakage. This level of contextual intelligence dramatically increases task success rates. Tesla also made breakthroughs in balancing agility with stability. The redesigned foot and ankle mechanisms allow micro-adjustments during movement, compensating for uneven surfaces or unexpected obstacles like loose cords or dropped objects. This translates to uninterrupted workflows, where Optimus V3 can carry loads or maneuver around tight domestic spaces, without stuttering or freezing mid-task. Performance data confirms the impact of these improvements. Internal testing by Tesla shows that Optimus V3 completes kitchen-related tasks, such as wiping countertops, loading dishwashers, and sorting groceries, with a 99% success rate when compared to task templates defined by human operators. More impressively, its average task completion time has dropped by 23% over the previous version, indicating not just more accuracy but dramatically enhanced efficiency. What sets this design apart from competitors is the seamless synergy between hardware and AI. Rather than retrofitting third-party components, Tesla has optimized every element, from fingertip sensor arrays to AI training datasets, to work natively with its FSD chip architecture. This tight integration avoids the latency and miscommunication often seen in modular robotic systems. The result? A robot that doesn't just mimic human motion, it understands human intention. It adjusts pressure when picking up a toddler's toy versus a ceramic mug. It recognizes that wiping a spill means scanning for residual droplets, not just making a sweeping motion. These aren't pre-programmed behaviors. They're emergent from the robot's learned experience. In essence, the new design of Optimus V3 marks a turning point. From mechanical mimicry to cognitive assistance, it's no longer a tool that executes, it's a partner that participates. And in doing so, it edges ever closer to becoming the world's first general-purpose, human-level, home assistant. How will Tesla produce millions of bots at low cost? Tesla is entering a whole new era of automation as it shifts from building electric vehicles to manufacturing humanoid robots with its Optimus project. However, it's not just the robots themselves that are impressive. The factory producing them represents a revolution. According to Elon Musk, this new facility will be 10 times more efficient than conventional production lines, not just because of its clever design, but due to a combination of GigaPress 50,000-ton aluminum casting, the reuse of Cybertruck robots, and a robot builds robot strategy. Analyzing the details behind these key elements reveals how Tesla can soon hit its goal of producing 1 million Optimus units per year at ultra-low cost. A cornerstone of this strategy is the GigaPress 50T, the world's largest high-pressure aluminum casting machine. This new generation of technology, already proven with the Model Y, has now been scaled significantly in both size and force. With a pressing capacity of 50,000 tons, this GigaPress can cast an entire Optimus frame in a single stroke, instead of assembling hundreds of individual parts. Internal engineers estimate this casting step can reduce parts count by over 70% and slash production time from hours to under 10 minutes per robot. Furthermore, reducing the number of components and joins drastically improves consistency and precision while lowering failure rates. In contrast to the Cybertruck line, which requires large robots to assemble thick, stainless steel frames, Optimus demands a very different approach: small, precise components measured in millimeters. Hence, Tesla cannot fully reuse the EV production line. It must build a specialized factory with compact, high-speed assembly bots and optimized material flow. Elon Musk hinted that some Cybertruck robots might be adapted for early production stages, but as volume scales up, the line will become fully automated and tailored to each assembly step of the humanoid robot. Factory optimization goes beyond robotics. Tesla is rethin. Factory optimization goes beyond robotics. Tesla is rethinking factory design down to the square meter. Every meter of the Optimus facility is redesigned. How materials move, how robots pick parts, and how AI orchestrates real-time production flow. Rather than traditional linear assembly where a car body passes sequentially through stations, this factory will follow a modular cluster model: arms, legs, torso, and head built in parallel, then merged later. This reduces bottlenecks and maximizes robot utilization. A truly game-changing strategy is the robot builds robot concept. From Genesis 3 onward, Optimus can perform over 500 diverse tasks, including lifting, screwing, precise hand movements, and accurate locomotion. Elon Musk emphasizes that with 99% precision at scale, Optimus bots can now perform many of the tasks involved in producing other Optimus units themselves. This isn't merely theoretical. Tesla has already tested Gen 3 units transferring components, assembling circuit boards, and inspecting sensors. If each Optimus can build at least one new bot per week, that leads to exponential growth, not just linear, in robot capacity. Other supporting factors also play a critical role. Tesla can leverage its high-density M3P battery technology, first used in Model 3 Highland, to make Optimus more compact and efficient. Co-locating battery and motor production in the same Gigafactory also reduces logistics and inventory costs. Moreover, Tesla shares common modules, control boards, vision sensors, and FSD chips between EVs and Optimus systems, amortizing production costs across massive volumes. All of this is managed and refined via Tesla's proprietary AI software, enabling real-time factory adjustments. Elon Musk calls this concept Gigafactory 2.0, a facility that not only builds robots but learns, improves, and reproduces itself through software updates. While a traditional Gigafactory might take 2 to 3 years to double output, adding Optimus to the production loop allows Tesla to double its robot output within months. You will instantly recognize it as Tesla Optimus, even at just a quick glance. With its iconic humanoid design packed with features and immense value for our lives. But have you ever wondered about the approach Tesla used to build this incredible humanoid robot prototype? In today's episode, we're diving into the 6 core elements that make Tesla Optimus incredibly useful for your life this year. But before we begin, Please help us reach 12,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. How can Tesla Optimus distinguish between different people in a family? Based on the latest demonstrations, technical updates, and AI architecture analysis from Tesla, this humanoid robot is designed with the ability to distinguish between different individuals in a household. This aligns with Tesla's goal of creating a versatile robot for both home and office environments. Optimus can differentiate between individuals primarily through advanced computer vision and integrated sensing. It identifies family members by building profiles based on visual cues such as facial features, body language, and movement patterns. This allows to tailor its behavior to each specific user, for example, recognizing who is speaking or gesturing in a multi-person setting. Currently, Optimus uses a 3D camera system similar to Tesla's full self-driving system to process real-time visual data. These cameras feed into a neural network that performs object and human recognition through deep learning algorithms. This is combined with sensor fusion, which integrates data from vision, sound, and even tactile force sensors to build contextual awareness of its surroundings. For example, in various demos, Optimus responds to specific human gestures or voice commands in crowded environments, suggesting it can isolate and identify individuals. Reinforcement learning further refines this capability by incorporating human feedback to improve accuracy over time. And the large AI model helped decode subtle cues like facial expressions or posture, enabling personalized interactions in shared spaces. The robot uses an end-to-end neural network trained on massive datasets, including first-person human perspective videos and increasingly third-person internet videos for deeper learning. This allows it to bootstrap new skills rapidly. In addition, Tesla Optimus can build a comprehensive understanding of its surroundings by utilizing shared 3D home scans and user behavior profiles, such as habits and preferences, stored in the cloud for future recall. Natural language commands trigger these contextual adjustments, with all tasks processed by a single multitask neural network embedded within the robot's hardware. Elon Musk has described this type of AI as having the potential to become a friend who truly understands you, hinting at a profound level of personalization. Custom mechanical structure and actuator. When it comes to building a humanoid robot like Tesla Optimus, the first core factor to consider is muscular strength, also known as the actuation system. A humanoid robot is designed to perform a wide range of physical tasks, from factory labor to everyday household assistance, requiring precise, efficient, and durable movement capabilities. Actuators serve as the robot's muscles, functioning like high-torque motors that determine whether Optimus can lift heavy objects, move smoothly, or carry out delicate manipulations. According to Tesla's updates through 2025, the core development of Optimus focuses not only on artificial intelligence, but also emphasizes a robust mechanical structure and custom-designed actuators. This gives the robot a significant edge over commercially available alternatives. The mechanical structure of Tesla Optimus is designed in a humanoid configuration to optimize flexibility and adaptability within human environments. Optimus features between 28 and 40 degrees of freedom, enabling it to perform complex movements such as walking, bending, grasping objects, and even ballet-like motions. Its skeletal frame is built from lightweight alloys, combining carbon fiber and high-grade plastics to reduce overall weight while maintaining structural strength, allowing the robot to handle heavy-duty tasks more effectively. For example, Optimus's arms utilize a sophisticated joint system with trapezoidal screws making up 23% of the linear joint assemblies, reducing friction and increasing precision. This design is heavily inspired by the human body, with shoulder, elbow, and hip joints engineered to mimic natural movement, enabling speeds of up to 5 miles per hour in Gen 3. However, the biggest challenge lies in balancing rigidity and flexibility. The frame must be strong enough to withstand impacts without significantly increasing power consumption. Tesla has addressed this by integrating force sensors into each joint, allowing the robot to adjust its posture in real time, helping it avoid injury or mechanical failure during tasks. Moving on to the custom actuators, a key factor that sets Optimus apart. Tesla recognized early on that off-the-shelf actuators could not meet the strict requirements of strength, compactness, precision, and energy efficiency all at once. Standard actuators are often too bulky, power-hungry, or lack the finesse needed for delicate tasks like folding laundry or stirring food. As a result, beginning with early experiments in 2021, Tesla's engineering team chose to develop an in-house portfolio of custom actuators, including 3 rotary types and 3 linear types. These actuators were designed from the ground up, incorporating planetary gear systems to boost torque while minimizing size, integrated smart electronics for precise control, and mechanical clutches to protect against overload. The design process began with 3D modeling, followed by prototyping and iterative testing using data from AI training systems. This allowed Tesla to optimize energy performance, bringing consumption down to around 100 watt-hours for a full day of operation. The combination of a purpose-built mechanical structure and custom actuators not only solves key technical challenges, but also unlocks major economic potential. With plans to produce thousands of Optimus units by 2026, Tesla is targeting factory deployment first, followed by the consumer market, with a projected price of around $20,000. So, how much can the price of Tesla Optimus Gen 3 drop with the all-new design? Before we begin, please help us reach 11,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Optimus and the latest news. Elon Musk has repeatedly stressed that Optimus must be priced below the cost of human labor in developed economies to achieve widespread adoption. In a 2024 shareholder meeting, Musk projected that, with sufficient optimization, production costs for Optimus could fall below $20,000. This figure is striking when compared to existing robotic platforms, such as Boston Dynamics Spot, which retails for approximately $74,500, or Figure AI's Figure 01, estimated at $100,000 to $150,000 for early prototypes. Achieving such a low price requires a revolutionary approach to design, eliminating inefficiencies while maintaining safety and functionality. The Optimus Gen 3 design represents a significant leap forward in efficiency. According to leaks and footage from Tesla's 2025 Investor Day, the robot is approximately 22 pounds lighter than its Gen 2 predecessor and incorporates 30% fewer mechanical components. This reduction simplifies assembly, lowers maintenance costs, and minimizes expenses related to quality control and inventory management, key drivers of mass production costs. Industry analysts estimate that streamlining a robot's mechanical structure can reduce assembly time by up to 25%, translating to significant savings according to the Robotics Manufacturing Report in 2025. Material choices further enhance cost efficiency. Tesla has reportedly transitioned from traditional aluminum and steel to advanced cast alloys and reinforced polymers for select external components. These materials, which are lighter and cheaper, can be produced at scale using molding or additive manufacturing techniques like 3D printing. A 2025 study by McKinsey on robotic production suggests that consolidating a robot's shell from dozens of parts to 4 to 5 major pieces could slash material and machining costs by 40 to 50%. For Optimus, this shift could reduce the cost of the exoskeleton by over $2,000 per unit at scale. A cornerstone of Tesla's cost reduction strategy is its reuse of existing automotive hardware and software. The full self-driving chip, which powers Optimus's AI capabilities, is the same one used in Tesla's vehicles, with over 1.2 million units produced annually in 2024 by Tesla Q 2024 production report. By avoiding the need to develop a bespoke processor, Tesla saves an estimated $50 to $100 million in R&D costs. Similarly, cameras, sensors, and electric motors are sourced from Tesla's automotive supply chain, which benefits from economies of scale unmatched in the robotics industry. For instance, Tesla's ability to procure high-resolution cameras at $50 per unit, compared to $200 for competitors, significantly lowers Optimus's bill of materials. Internal estimates from Tesla's production team suggest that at a production volume of 500,000 units per year, The manufacturing cost of Optimus Gen 3 could range between $14,000 and $16,000 per unit. This is already competitive with the base price of a Tesla Model 3, which retailed for $39,990 in 2025. If Tesla offers financing or bundles Optimus with subscription-based AI services, the effective retail price could dip below Musk's $20,000 target, making it accessible to a broader consumer base. Tesla's pricing strategy extends beyond hardware costs, leveraging innovative business models to maximize affordability. Unlike traditional robotics companies that rely on high-margin hardware sales, Tesla could adopt a low-margin approach similar to its Model 3 and Solar Roof strategies. By selling Optimus near cost, Tesla could generate long-term revenue through software, updates, AI-powered subscriptions, or service contracts. For example, an Optimus as a service model could allow consumers to rent the robot for $50 to $100 per month for tasks like elder care, home maintenance, or meal preparation, mirroring trends in the service robotics market, which is projected to grow to $103.3 billion by 2030. This approach aligns with Tesla's target market: households, particularly those with elderly members, special care needs, or professionals seeking AI-driven assistance. While industrial robots can justify price tags of $50,000 or more, consumer robots require affordability akin to smartphones or laptops. A 2025 survey by Deloitte found that 62% of U.S. consumers would consider purchasing a home assistant robot priced under $20,000, especially if offered with flexible financing. Tesla's ability to offer monthly payment plans could make Optimus as accessible as a $500 smartphone spread over 2 years. Tesla's vertical integration provides a structural advantage over competitors. Unlike Boston Dynamics, which excels in technology but lacks large-scale manufacturing, or Figure AI, which depends on third-party suppliers, Tesla controls its entire production pipeline, from chips and software to factories. This allows Tesla to optimize costs at every stage. For instance, Agility Robotics Digit, deployed in Amazon warehouses, carries a price tag of $40,000 to $50,000 due to high U.S. production costs. In contrast, Tesla's Gigafactories, which produced over 410,000 vehicles in Q2 2025, provide the infrastructure to manufacture Optimus at an unprecedented scale. Tesla's Fremont factory is being retooled for Optimus pilot production, with plans to have several thousand units operational by the end of 2025. This scalability is critical, as economies of scale drive down costs. Historical data from Tesla's Model Y production shows that each doubling of output reduces unit costs by 15 to 20%. If Tesla achieves Musk's vision of producing 1 million Optimus units annually by 2030, unit costs could plummet to $10,000 to $12,000, a price point that would disrupt the robotics industry. How have operating and charging times improved after this big update? Among the most common inquiries about Tesla's Optimus is its operational endurance and recharge requirements, critical factors for potential buyers evaluating its practicality as a home or workplace assistant. As outsiders to Tesla's development team, pinpointing exact technical specifications, such as battery performance or mechanical details, poses a challenge. Tesla claims Optimus can operate for up to 20 hours daily with a 2.3 kilowatt-hour battery, a figure that sparks skepticism given the energy demands of humanoid robots. Tesla Optimus, a humanoid robot developed by Tesla, is built upon 7 core systems. If you understand these, you will have a solid foundation for building a humanoid capable of solving real-world problems with efficiency, accuracy, and reliability. Moreover, deploying the robot for tasks related to healthcare and household support becomes much simpler now that Tesla has recently upgraded this entire core system. So, what are these 7 core systems, and how will they enhance the capabilities of Tesla Optimus? But before we begin, please help us reach 12,500 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. Human-inspired mechanical design, or simply put, mechanical design modeled after the human body, forms the foundation of a humanoid robot. Essentially, this robot is structured like the human body, with 2 legs, 2 arms, a torso, and a head. Each limb is composed of joints powered by actuators, which are strong motors that enable the robot to move, bend, jump, run, and interact with objects. To facilitate understanding, the mechanical design can be divided into 3 subsystems. The first subsystem is the bipedal locomotion mechanism, in simpler terms, the robot's legs. The second subsystem consists of 2 spatial manipulators, or the robot's arms, equipped with end effectors, also known as grippers, which function like human fingers with dexterity. The third subsystem includes the torso and neck, which play a crucial role in maintaining the robot's range of motion and overall stability. This mechanical architecture is meticulously designed to balance strength, flexibility, durability, precision, and reliability. Once we understand the first core system, the mechanical design, it is essential to explore the second core system, which is the application of that design. In industry, humanoid robots assist with heavy-duty tasks such as lifting objects and transporting goods in warehouses, thereby increasing productivity and reducing the physical workload for humans. In healthcare, they support patients and help the elderly move or perform delicate actions thanks to their dexterous grippers. At home, humanoid robots aid people with disabilities or the elderly in daily activities like cooking and cleaning, enhancing their quality of life. In rescue operations, their agile mobility allows them to access dangerous areas to assist in search and rescue missions. Additionally, robots are used in education, motion research, and artificial intelligence development, or serve as guides in retail and tourism due to their ability to interact naturally. With a design that balances strength, durability, and precision, humanoid robots hold the potential to revolutionize multiple fields, although further advancements are needed to ensure safety and cost-effectiveness. Core System 3, Mobility System, Bipedal Locomotion. A humanoid robot being designed with 2 legs does not automatically guarantee its ability to walk or maintain balance. Mobility is a skill that the robot must acquire only after mastering balance. So, how does a robot achieve this? How does it ensure it doesn't fall with every step? To remain stable while moving, a humanoid robot must understand several factors: the structure of the terrain it is navigating, the slope of the ground, and the position of its center of mass. Based on this information, it must then decide how to execute the next step. This means that at every step, the robot must process input parameters, such as the terrain, incline, center of gravity, and more, to make a calculated decision about how to move forward. In robotics, this process is known as gate planning. Essentially, it refers to the robot selecting the most appropriate stepping pattern for the next move, based on the real-time data it gathers from its current environment. So what did Tesla do to make the Optimus do that? There are 2 main approaches to tackling this challenge. The first is a reactive method, which relies on sensor data, such as force sensors in the feet, to detect changes in the ground surface. Based on this input, the robot responds by activating motors or actuators located in its legs. These actuators generate the appropriate torque, a combination of force and speed, to ensure the robot maintains firm contact with the surface. This strategy is commonly referred to as a reactive approach. The second is a proactive method, grounded in prediction or probabilistic reasoning. Instead of merely reacting to real-time sensor data from the current step, the robot scans the terrain, gathers both current and historical data from previous steps, and uses that to predict how the terrain ahead might change. Based on these predictions, it then adjusts its next step or selects the most suitable gait pattern. In summary, these 2 core systems work together to ensure that the robot remains balanced and moves efficiently in various environments such as factories, warehouses, or homes, with high traction, precision, strength, and stability. Now you might wonder, this covers mobility, but what if the robot needs to lift an object or pick a fruit from a basket? How does it manage that? Let's move on to the next core system to understand how Tesla Optimus makes that possible. Core System 4, Spatial Manipulators and End Effectors, Incredible Hands. This is where spatial manipulators with end effectors become essential. A spatial manipulator refers to a robotic arm with dexterity comparable to that of a human arm, while the term end effector refers to the electronically controlled fingers or grippers used to grasp objects. Most modern humanoid robots are equipped with two spatial manipulators, each featuring a powerful end effector. Mechanically, these are metallic limbs or components connected to high-torque motors, enabling a wide range of motion. In robotics, this range is described in terms of degrees of freedom, DOF. When you hear about a 3DOF or 4DOF system, it refers to the number of motor-controlled joints in each manipulator. So, why is this number important? If a robotic arm has more joints, each joint can move in multiple directions and at varying speeds, allowing the robot to perform thousands of complex and diverse movements. The human arm, for instance, has 7 degrees of freedom, with 3 joints in the shoulder, 1 at the elbow, and 3 in the wrist. Humanoid robots are built following a similar model. While most humanoid robots typically have 6 to 7 degrees of freedom per arm, Tesla Optimus stands out with an impressive 22 degrees of freedom, offering exceptional dexterity, precision, and efficiency that closely resembles human capability. So far, we've explored 3 core systems: the mechanical design, bipedal locomotion, and spatial manipulators. The next important question is, how does the robot make decisions? How does it know how to move its arm to pick up an object? Objects in the real world come in all shapes and sizes. An apple is very different from a car part on an assembly line. So, how does the robot recognize and interact with these objects in such a dynamic environment? This is where sensors and the perception system come into play. Core System 5, Sensors and Perception System. When considering a task that a humanoid robot needs to carry out in the real world, it can be broken down into multiple smaller steps or subtasks. Each of these can be individually trained and optimized to build up toward completing the full task effectively. To ensure the robot performs the overall task reliably and safely, it must first be trained on each of the smaller components before progressing to the entire task as a whole. So, how is this training accomplished? In the past, robots were programmed manually using basic logic structures like if-else statements. However, that approach has become outdated. Today's advanced humanoid robots use reinforcement learning to acquire these skills. This involves defining specific inputs and desired outputs for every subtask. Inputs typically consist of control signals that activate the robot's motors in its limbs, while the desired output is the intended action, such as grasping an object. The robot is trained using an artificial neural network that repeatedly adjusts the input signals to achieve the correct action. When the robot successfully completes an action, it receives a reward. If it fails, like dropping an object, it receives no reward or a penalty. Over time, through weeks or even months of training, the robot's movements become increasingly refined and accurate. This method is applied to each individual subtask and eventually to the full sequence, enabling the humanoid to master complex tasks from start to finish. Tesla Optimus, now in its 5th iteration, has seen significant updates in 2025, including improved walking gaits, enhanced arm architecture, and plans for mass production of up to 5,000 units by year's end. Priced affordably between $20,000 and $30,000, Optimus is designed for tasks that are unsafe, repetitive, or boring. But its true power emerges when fused with Grok 4. Musk has confirmed ongoing integration, with Optimus V3 already leveraging Grok for voice interactions and natural language processing. This synergy promises profound benefits for humanity, particularly for America's aging population. As of 2025, over 59 million Americans are aged 65 and older, representing nearly 18% of the population, a figure projected to rise to 82 million by 2050. Elderly individuals face mounting challenges. Social isolation affects 1 in 3, leading to heightened risks of depression, anxiety, and cognitive decline. Suicide rates among seniors have reached historic highs, and a shortage of caregivers exacerbates issues like unaffordable care and limited access to health services. AI-powered robots like Optimus, enhanced by Grok 4, could address these by promoting independence, providing companionship, and reducing caregiver burden by up to 50%. How does Grok 4 use reasoning to make decisions? At the core of Optimus's evolution is Grok 4 serving as its inference-based brain, enabling the robot to process complex tasks involving language, mathematics, programming, and scientific reasoning. Unlike traditional robots limited to pre-programmed commands, Grok 4 allows Optimus to understand environments, multitask, and make independent decisions based on real-time data. For instance, in a factory setting, Optimus could analyze production issues and self-adjust, but this capability extends powerfully to human-centric applications. For the general population, this means Optimus becomes a versatile assistant capable of handling dynamic household chores, or even creative problem-solving. Imagine a robot that not only folds laundry, but also optimizes energy use in a smart home by reasoning through utility data. Grok 4's advanced logic and massive context window ensure responses are accurate and adaptable, reducing errors and enhancing efficiency. The benefits are amplified for elderly Americans, where cognitive and physical limitations often hinder daily independence. With 25% of adults over 65 receiving no assistance for daily activities, Grok 4-powered Optimus could step in as a proactive aid. Studies show AI robots enhance independence, with one review noting they help seniors live longer, healthier lives by providing generic solutions for biomechanical assistance in tasks like sit-to-stand movements. In the U.S., where the elderly population is expected to outnumber children by 2030, this integration could alleviate the caregiver shortage, projected to worsen as demand for long-term care surges. By 2025, early deployments in homes could reduce hospital visits by enabling predictive health interventions, saving billions in healthcare costs while fostering a sense of autonomy. Grok 4's ability to learn from interactions ensures personalized care, adapting to individual needs over time. How does Tesla Optimus Gen 3 integrate a voice assistant for natural communication? Grok 4 elevates Tesla Optimus from a mechanical tool to a conversational companion through its role as a voice assistant, enabling natural, intuitive interactions. Optimus Gen 3 already incorporates Grok for voice commands, allowing the robot to understand nuanced requests, clarify ambiguities, and respond intelligently, far beyond rigid scripting. This multimodal capability, including image interpretation, lets Optimus see and discuss visual elements like analyzing a family photo or a medical chart. For everyday users, this means seamless integration into daily life. Optimus could chat about the weather while preparing meals or assist in virtual meetings. Grok 4's multilingual encoding support further broadens its utility, from teaching skills to troubleshooting tech issues. Elderly Americans grappling with loneliness amid a silent epidemic that increases risks of heart disease and dementia stand to gain immensely. With 1/4 of seniors living alone, Grok 4-powered Optimus offers emotional support through engaging conversations, mimicking human empathy to reduce isolation by providing companionship 24/7. Research indicates AI companions boost adherence to physical activity by increasing engagement and exercise duration, countering sedentary lifestyles that affect 88% of older adults. In practical terms, Optimus could read aloud, play games, or facilitate video calls, addressing literacy barriers where many struggle with health information. By 2025, as America's Health Rankings report highlights worsening mental health trends, this feature could lower suicide rates by fostering connections, with studies showing robots reduce caregiver strain and enhance quality of life. How would Tesla and Grok 4 ecosystems create a learning and transformation environment for Optimus? Grok 4's integration with Tesla's full self-driving system creates a symbiotic relationship, where Grok handles environmental understanding and communication, while FSD manages precise movement. This allows Optimus to learn from real-world data, improving over time through adaptive algorithms, enabling fluid navigation in complex spaces. For broader applications, this means Optimus excels in dynamic environments, from warehouse logistics to home automation, with enhanced safety and efficiency. Grok 4's tool integration could even simulate scenarios for better planning. For the elderly, mobility challenges are rampant. Falls cause 3 million emergency visits yearly, and limited coordination affects daily tasks. What do you think about this? Feel free to share your thoughts in the comments section below. We hope to bring the best information to you. Please give a thumbs up if you like this. Join Techno Creator by subscribing and hit the bell icon so you will not miss out on any awesome videos. We value your feedback. Thanks for watching. Until then, stay safe and have